Hello everyone, this is Fahad and this would be an introductory lecture for AS chemistry, and we're going to start off with atomic orbitals. Now, this is the basic concept behind the whole of chemistry that you're going to start learning in AS. And when we talk about atomic orbitals, we did study orbitals in O levels. Now, if you recall what you did in O levels, you had nitrogen, which had 7 electrons. Now, nitrogen has 7 electrons. The electronic configuration for nitrogen was that in the first shell there were 2 electrons, and in the second shell there were 5 electrons. So you had 2 electrons in the first shell and 5 in the second shell. Now, there was a simple rule in O levels that electrons were divided into shells. You had shell number 1, the first shell, and it had 2 electrons in it. Then you had shell number 2, which had 8 electrons in it. Now, shell number 1 was also called the K shell. Then you had the L shell, and so on and so forth. So as you moved away from the nucleus, the energy of the shells kept on increasing. So you had higher and higher energy shells as you moved away from a nucleus. And a simple rule for determining the number of electrons in a shell was 2n squared, which basically gave you an idea of the number of electrons in a shell. And if you observe this formula carefully, n stands for the number of the shell. For example, if it's the first shell, then if you put n is equal to 1, that would come out to be 1 squared is 1, 1 into 2 is 2. So the first shell, which is the K shell, has 2 electrons in it. If you look at the second shell, then the second shell has 2 squared into 2, that's going to be 8 electrons. And if you look at the third shell, that's going to have 18 electrons. 3 squared is 9, and 9 into 2 is 18. So this 2n squared is a formula that you must keep in mind that gives you the number of electrons in a shell. So now let's draw the structure of an atom based on what we did in O levels. So you had nitrogen, and this is the nucleus of nitrogen, and there were 2 electrons in its K shell, which is the innermost shell, the first shell, or the lowest energy shell. Similarly, there was another orbital around it, and there were 5 electrons in that orbital. So this was the representation of a nitrogen atom. Let me write this down. This is shell 2, or the L shell, whereas the inner one was shell number 1, or the K shell. So this was a very basic representation of how an atom looked like and how electrons behave. Now there were certain simplifications that were not true. One is that it is shown that an electron is behaving. It's a single entity. Electron is represented as particles. And the second probably is that electrons are shown orbiting the nucleus. It's like the solar system, that planets are basically orbiting the sun, which represents the nucleus over here. So both of these assumptions are basically incorrect. The only thing that you can actually take away from this model is the energy levels. The 2 electrons are at a lower energy level. There are 5 electrons at a higher energy level. That's probably the best that you can actually take away from this model. So let's go towards a more complicated model. Now, before moving on, we must know what an electron looks like. We need to figure out what is the shape of an electron. Now, there's a term called wave-particle duality. What that basically means that if you have an electron, it's going to behave as a wave, and it behaves as a particle as well. Now, waves and particles are totally different species. For example, if you have a wave, then it won't have any precise location. For example, if there's a rope, let's say this is a rope tied to the end of a wall, and if I start shaking the rope, there's going to be a wave produced, and it's going to travel along this rope and hit the wall, and then it's going to get reflected back and come back to me, and so on and so forth. So the wave is going to be traveling forwards and backwards at the same time. This is called a standing wave. You don't need to actually go into a lot of detail about the concept, but now the point is, if somebody asks you where the wave, at which point is the wave located, you can't really figure it out because it's spread out throughout space. Whereas particle, when you talk about a particle, it has precise location. So it has a precise location, a precise point in space where a particle is located. Now, one way to describe an electron is when it's moving, it's behaving as a wave. So when it's moving, it's behaving as a wave, and when you think of it as stationary, it's behaving as a particle. So when it's moving, you don't know where it's going to be located. It's going to look like this, a standing wave which is going back and forth in a specific region. So it has no precise location, or if it does have and there are other certain points which we need to discuss about the particle nature of an electron. When you think of it as a particle, then always remember an electron is always going to have a -1 charge, which in terms of coulomb is 1.6 into 10 raised to the power minus 19 coulombs. Now, this is a very discrete value. Discrete means it's a very precise value. It never changes. It's like a particle is not going to change its mass. It's you can use that analogy to describe an electron. So it's always -1.6 into 10 to the power minus 19 coulomb. And if an electron gains energy, then only this much charge is going to gain energy. So it is very specific when it comes to charges. So there's certain behaviors of an electron where it behaves as a particle, and there's certain behaviors of an electron where it behaves as a wave. One way to describe the wave is for example, if you have light passing through, and there are two slits. There's a wall and there are two slits over here, and if light is passing through, it is able to pass through both slits at the same time. This is called diffraction. You'll probably study this later in physics. Now, waves have this property that they can go through two slits at the same time. Similarly, an electron has that property as well. When it's traveling like a wave, and it can go through two slits at the same time, and that's called diffraction. So diffraction applies to electrons as well. So so after telling you all this, we still haven't really figured out what an electron looks like, whether it's a wave or it's a particle. Another thing about waves is that when you think of waves, different waves can overlap and they can still be unique. For example, at sea, when you're at sea, if one wave is traveling from north to south, let's say one wave is traveling from north to south, and another wave is traveling from uh, let's say this was north to south, and this was east to west. Now, if there are two waves traveling, then those two waves will keep on traveling. They will overlap, superimpose at some point, but they will still remain unique. So, but on the other hand, if an electron was a particle, then those particles would collide and they would obviously change. They would destroy themselves, or something else would happen, or they would get deflected. But when you have electrons traveling, they can overlap with each other and still remain unique. Now let me introduce you to the concept of orbital. Now, an orbital is not, it's not like it basically means like an like an orbit or similar to an orbit, but it's not actually an orbit. So electrons basically reside in orbitals. So in an atom, electrons reside in orbitals. And what are orbitals? They're basically regions in space where you might find an electron. So there are regions in space where you might find an electron. Now, those regions in space are located around the nucleus. The nucleus is positively charged, and let's talk about one. Take the example of a p orbital. Now, a p orbital has this shape. Now, if you look at a p orbital, it's basically dumbbell shaped. This is called dumbbell shaped. I haven't drawn a very accurate, precise shape right now. Uh, so this looks like a dumbbell. I mean, there's a now this is a region around. It's lying to the left. This specific region around around the right of the nucleus, and there's a region around the left of the nucleus. So if an electron is residing in this region, then that electron could be found anywhere in this region, and it could be existing as a wave or as a particle. And since an electron is both, it's going to be a wave particle duality function, which means that you would find an electron over here. You don't know what it looks like, whether it looks like a wave or a particle. So the basic idea of an orbital is that it gives you the location of a region in which you might find an electron. So this is an example of a p orbital. Similarly, there are other shaped regions around the nucleus where you might find an electron. For example, there is an s orbital. An s orbital would look something like this. There's a nucleus in the center, and there's a spherical region. There's a spherical region around the nucleus where you might find an electron. So an electron might be existing in this region, in this entire region, either as a wave or a particle. So this is the shape of an s orbital. Similarly, there are other regions around the nucleus which are uh, some are called d orbitals. I will quickly draw the shape of all the d orbitals. For example, d orbitals are not in a syllabus, so you don't need to remember what the shape is going to look like. Um, let's say this is the x-axis, this is the y-axis, and this over here is the z-axis. So if you have a d orbital would look like this. This is the center of the nucleus. There's a region around here where you might find an electron. There's a region around here where you might find an electron. There might be a region around here where you might find an electron. Similarly, there would be a region around here where you might find an electron. This is actually called the dxy orbital. Let's talk about another d orbital or another region in space where you might find an electron. It looks like this. There's a nucleus, and there's a region on top of that nucleus, and there's a region at the bottom of the nucleus where you might find an electron, and it's lying on the z-axis. And there's another donut-shaped lobe around the nucleus where you would be, where there's a chance, there are chances that you might find an electron there as well. So an electron could reside in a region like this. So if you're probably getting an idea that orbital is simply a region where you might be able to find or locate an electron. So electrons around, we discussed previously. We discussed the case of nitrogen where it had two electrons in the inner shell, and it had five electrons in the outer shell. Now we're going to take this concept and we're going to turn it onto its head, and we're going to show that electrons, instead of residing in shells, specific shells, electrons basically reside in orbitals, and they don't orbit, they don't move around. I mean, there might be an electron present in this entire region over here. If it is present in this region is called the dz square orbital. So if it is present in this region, then that electron will be present in the dz square orbital. Similarly, if an electron is present in this region, then it would be present in the dxy orbital. An electron is present in the s orbital, then that region is called the s orbital. Similarly, you have the p orbital.